Good afternoon, everyone. I am Abhishek Vijay Gopal and I head CySecK's academic programs focusing on skilling and promoting research. We'd like to welcome all of you to today's webinar, which is the eighth and final webinar as part of the Digital Defenders Cybersecurity Masterclass and Capture the Flag Competition 2023. Thank you for joining us. The Digital Defenders CTF 2023 is being organized by CySecK in association with Cisco Systems India Private Limited, Cisco CSR, and the Center for Networked Intelligence at the Indian Institute of Science in Bengaluru. Although this webinar is a part of the Digital Defenders CTF 2023, both CTF registrants and non-CTF participants are most welcome to attend this webinar. So this slide shows the schedule of the Digital Defenders CTF 2023. So we are now in after this, we are going to have the CTF intro session on July 5th. However, only the top 500 participants who qualify to play the CTF will get the intimation for the same. So I will very briefly go through the exciting prizes on offer for the CTF 2023 participants. I've done this on earlier webinars and will try to therefore be as brief as possible. The creme de la creme is the internship opportunities in partner organizations. So the shortlisting for an internship opportunity, however, will involve additional prerequisites to be met by the winners of the CTF and will be solely at the discretion of the partner organization, whose decision in this regard will be final. Also, there are exciting prizes worth a total of Indian rupees 4 lakhs, which are going to be won by the top 25 candidates who are ranked in the top 25 at the end of the CTF. So there are three first prizes with a cash component, a voucher for Hack the Box, and a Raspberry Pi that's valued at 40,000 rupees each. There are 5 second prizes, which comprise of 10,000 rupees cash component, plus a voucher for Hack the Box, plus a Raspberry Pi, and valued at 25,000 rupees each. There are 7 third prizes, which comprise of only Raspberry Pi and Hack the Box. They're valued at 15,000 rupees. And there is also 10 participation prizes of Raspberry Pi, which are valued at 5,000 rupees. So the prizes will be distributed only after suitable verification requirements would be met by the participant, as would be decided by the organizers. And the decision of eligibility for the award of a prize would be solely again at the discretion of the organizers, which would again be final and binding. So we are now in the 64th webinar of the Samgacchadhwam series. And last year, the government of Karnataka took an exciting step by providing cybersecurity as a specialization option for the diploma students. And we at CySecK helped draft the syllabus for this course. Whilst we are sure it will be of assistance to the students who have opted for this course, we are nevertheless confident that it will help other students or working professionals who are interested in cybersecurity as well. Cybersecurity is not just a critical domain, but is also an evolving field. So we will aim to provide an overview on each of these domains with opportunities for conducting hands-on activities and with some pre or post read, which would help all of you to go into further depth. We hope that this will kindle your interest to explore further. So the next event after today's masterclass webinar would be the CTF intro session, and the CTF intro session is scheduled for 5th of July, that is Wednesday, at the same time between 3:30 and 5 p.m. And I'd again like to repeat, only the top 500 candidates who would be eligible to participate in the CTF based on their assessment scores over the 8 webinars would receive the intimation to join that session. That is not a session open for everyone. So I would now request all of you to please subscribe to our YouTube channel. Through this YouTube channel, you can see the previous webinars that CySecK has organized. You will find links to this on the CySecK website as well as on our YouTube channel. And if you subscribe to our YouTube channel, you will get to know when new recordings are out, and it will help us to gain better traction and visibility. So I'll just pause a moment here on this slide, and I request all of you to please take a screenshot. We have shown the different social media handles of CySecK, and request all of you to please follow our social media handles so that you can remain abreast of all our events. So on on Twitter and on Instagram, we are at the rate CySecCoe. On Facebook, we are at the rate CySecKar, and on LinkedIn and YouTube at the rate CySecK. Our website is cs-coe.isc.ac.in. So I'll just pause a moment here so that you can take a screenshot of this slide and make a note of all our social media handles. Thank you. I'll come to the scheme of webinar and assessment. So we have webinar number 64, which will be delivered by the speaker, Mr. Pagilla Manohar Reddy. It will be followed by a Q&A. And the Q&A will be moderated to group questions of a similar nature. So you're requested to type in the questions in the Q&A section. To access the Q&A section, what you would need to do is look at the right hand bottom part of your screen where you can see 3 dots. Please click on the 3 dots and expand the Q&A section, which appears with an arrow next to it, and ensure that you type in your questions in the Q&A box. It will then be visible to our moderator, Mr. Kaushik Gattigar, who will then group the questions accordingly and pose them to the speaker at the end of the webinar, in the sense, once the speaker completes his presentation. Then this will then be followed by the link to the assessment, the one of the most important exercises. It will be provided at the end of today's webinar. So we will post the link to the assessment in the chat box, but we will also post the link to the assessment on the webinar homepage, where it will remain active for the next 24 hours since it is announced. So it will remain active for 24 hours, and the recording of the webinar should reach our YouTube channel about 2 to 3 hours after completion of the webinar. So those CTF registrants who are unable to attend the webinar live due to prior academic commitments are welcome to view the webinar again on our YouTube channel and to attempt the assessment. Please note that the assessment itself contains only 15 questions, and therefore I'd request you to please take your time, see the webinar, clarify all your concepts, and ensure you attempt all the 15 questions. It is to the advantage of the candidate to attempt as many questions as possible, so that it will give the candidate a chance to maximize his or her score and maximize his or her chance for getting selected among the top 500 participants who would be eligible to play the CTF between 6th and 9th of July. So the assessment, like I mentioned, will be kept open for 24 hours post the webinar, and it will be followed by webinar feedback. Some of you might get some qualitative questions asking about the feedback and how we can improve the content and delivery of our webinar. So we take the feedback quite seriously. So we request you to please answer those questions in all sincerity. And since the assessment is being run through Google Forms, we request you to please use a Gmail ID to access the assessment. Now remember that we've got queries from some participants saying that they did not use a Gmail ID to register for the CTF, or that their email ID registered with CySecK on the CySecK website is not a Gmail address. There is no problem, because the assessment form itself has a field called email ID, in which you are required to enter the registered email address with which you have registered either for the CTF or on the CySecK website. We request all participants to adhere to this strictly because it would be our only means of verifying that identity and score of the participant in case of any issues or in case of any disputes. So if you ensure that you have consistently used the same email address with which you have registered for the CTF or on the CySecK website, then you can rest assured that all your score performances are going to be taken into account while determining your eligibility to participate in the final stage in the final CTF. So one more request would be to please refrain from using inappropriate language in the chat or in the Q&A section or the Q&A window while asking questions. In case we encounter some repeated instances of inappropriate behavior, then the administrator is at liberty to evict the troublemaker from the session. So we request you to please avoid creating or getting into such a situation. So let us now briefly go through what is the topic and content, expected content of today's webinar. So the topic of today's webinar is Cryptography Part 2, 8th and final Masterclass webinar as part of the Digital Defender CTF Competition 2023. So during this webinar, the speaker, Mr. Pagilla Manohar Reddy, will dive deeper into advanced encryption techniques and explore RSA, modular arithmetic, AES, and block ciphers. So during the first part of the webinar, he will unravel the mysteries of RSA and modular arithmetic and introduce the concept of modular arithmetic and its relevance in encryption algorithms. Next, he will delve into RSA, which is a widely used asymmetric encryption algorithm, and you will gain a comprehensive understanding of how RSA works and its key components. To reinforce your knowledge, we will engage in a hands-on RSA key generation exercise, allowing you to generate your own RSA keys. So therefore, it is recommended highly that you join this webinar using a laptop and not a mobile phone. Moreover, you will explore the vulnerabilities of weak RSA implementations through breaking a weak RSA exercise. There will be live demonstrations which showcase the process of cracking old RSA certificates and therefore highlighting the importance of robust encryption practices. In the second part of the webinar, the focus will shift to AES and block ciphers. So you will be presented with real-world examples of AES implementation, shedding light on its significance in modern cryptography. Delving into the inner workings of AES, you'll explore the encryption and decryption processes with a specific focus on the ECB mode. And furthermore, you will be provided with simple exercises to familiarize yourself with AES and its application. So by the end of the webinar, you are expected to have a solid understanding of advanced encryption techniques, including RSA, modular arithmetic, AES, and block ciphers. You will also gain practical experience through hands-on exercises and live demonstrations, equipping you with the height of knowledge to implement robust encryption practices and to safeguard sensitive information. So at the end of this 8th webinar, the top 500 CTF registrants in terms of aggregate assessment scores would be invited to play the CTF. There would be a pre-CTF introduction session, as I mentioned, on 5th July 2023, Wednesday, between 3:30 and 5 p.m., which will be held by experts from Team BIOS, which is the premier CTF team in the country. And the top 500 participants only will receive a mail inviting them to join this introductory session. So it is now time for us to introduce to you our speaker for today, Mr. Pagilla Manohar Reddy. Manohar is a consistent CTF player focusing on cryptography as his primary interest. He is currently researching on lattices and working on his personal blog to help beginners enjoy cryptography. He also published a research paper titled Attacks on Elliptic Curve Cryptography Implementations in SageMath. He is now pursuing his third year in the Bachelor of Technology course with a computer science and engineering specialization at Amrita Vidyapeetham in Amrita, Puri. So I'd like to welcome our speaker, Mr. Pagilla Manohar Reddy. Manohar, I request you to please turn on your camera and to share your screen. And I will stop sharing my screen now. Thank you.
Thank you very much, Mr. Abhishek, for the warm welcome. I appreciate everyone for making till here for this session. As you know, today is the last technical session, I really congratulate everyone for making till here, and also, like, wish you better luck for your upcoming CTF. So yeah, let me just quickly share my screen. Yes, I hope my screen is visible.
Yeah, I'd just like a few participants to please confirm that Mr. Manohar Reddy's presentation is visible, please. You can send a positive reaction or you can put a message in the chat. Okay. Yeah, it is visible, Manohar.
Okay. Yes. So great. So I hope everyone is active right now. So yeah, let's dive in. This is the part 2 of the cryptography session, and the part 1 has taken by speaker Sayed Samuel. He has taken the part 1 of the session where it consists of what introduction to cryptography is, what is encoding and encryption, what is the difference between them, what is binary, octa, hexadecimal, all these things. So I hope you have looked into Julian cipher, Caesar cipher, and all Enigma. Quickly, I'll share you an interesting fact. I hope you have seen the image in the last PPT where there is a typewriter kind of thing under the heading Enigma. So actually, Enigma is a really, it's a thing which is used in World War II. It is actually built by Alan Turing. If you know who Alan Turing is, he's also called as father of computers. Yeah, he is the one who has invented the first computer, which has just forward and backwards. So Alan Turing has invented, Alan Turing has cracked this enigma for the first time, where the enigma has been used by Nazis to encrypt their messages, and they have made a very big rotor machine kind of thing to crack this enigma, which has like a huge number of settings. You can't even imagine. In modern day computer system, we have these CPUs, RAM, GPU, everything, all these things, which can actively perform. But during 1940s, it is really difficult. There is not even a computer with 32 kilobyte RAM, I guess. Not even 32 KB RAM. It's a very great thing. So that is how interesting this encryption and decryption and cryptography is. So yeah, okay. Keeping that aside, this is the overview. Today we are gonna look into RSA and modular arithmetics, introduction to modular arithmetics, what RSA is, how it works, how do we generate key generations in RSA, and we'll look into a short exercise where I'll be doing with you, and breaking the weak RSA, weak encryption system in RSA, and also demonstrating a RSA certificate, which is very weak, and how do we gain access on it, and how do we actually decrypt the messages which is encrypted with those certificates. So yes, and later in the session we'll be looking into AES and block ciphers, an example and examples of real world AES and block ciphers, how it works, how the internal system of AES and block ciphers are, how the encryption and decryption in ECB mode is, and a simple exercise followed by. Yes. Okay, then yeah, we'll quickly get started with what is modular arithmetics. So, like modular arithmetics sound so magical, but we use this technique in our day-to-day life. Let's say the time is right now something around 11 p.m. And what we say is, okay, there might be a movie releasing in 3 hours from 11 p.m. or there is a movie show which is 3 hours from 11 p.m. We don't tell that the time is the movie release time is not 13 p.m. We tell it's a 2 a.m. Basically, when you look into your watch, all the numbers are in a clockwise manner. So, it is like 12, 1, 2, 3, 4, 5, 6, so on up to again 12. So, whenever you're looking into time, you basically look into your watch, even if it's noon or if it's evening or if it's morning, you just differentiate with AM or PM, and then you will call the number by subtracting it by 12. Let's say there is a 24-hour time format, which is like you represent time in 24 hours. So we call 16 in 24-hour time format is actually 4 a.m. in 12-hour time format. What you're doing there is you took a number 16 and then you have modded the number 16 with 12 unknowingly. I mean, this is a practice which we have been doing since our childhood. That is how we see time. Basically, modular mathematics also, it's the same thing. Arithmetics, which limits the range of numbers wrapping around and then limit its reach. So let's say whatever the number size is, you try to represent in the circle of numbers. So if I tell the time format is somewhere around 25, I tell the time is 25, then you'll quickly understand, okay, time format cannot be 25, it should be 1 p.m. because either it should follow the 12-hour time format or it should follow the 24-hour time format. So you will be understanding that, okay, 25 means 1 a.m. That is how this modular arithmetic works. So it is the same thing, like it is just wrapping around the number in that circle of numbers. Uh, so the advantage in modular arithmetics is how large the number is. It all depends on the mod thing. So typically the modular, when we are performing a mod arithmetic on a number, we represent it like 2 mod 12. So basically, this mod tells us that we are performing a modular operation on that particular number, or it has been performed, or it makes us clear that the number which is there in front of mod is also lies inside the number which is after the mod. A simple example to tell that the number after the mod is basically like, you know, it actually defines all the numbers which are there in that field, or all the numbers which are present in that number system lies only between 0 to 12. There is no number called 13 in the modular arithmetic of 12, because if you take 13 and when you try to subtract 12 from it, when you try to divide 12 with 12, you get a remainder 1, which means basically you can tell that, okay, this 13 mod 12 is same as 1 mod 12 because it leaves the same remainder. That is how usually the modular arithmetics are performed. Let's say another number, let's take a modular field of 6, or let's take a 5. Now I'll take a number 24. So can someone quickly put chat on chat, like what is the remainder when you divide 24 with 5 or something? Maybe if it's possible. 24. 24 divided by 5. Yeah, it's 4. So yeah, yes, it's 4. Basically, then you can tell that 24 mod 5 is equals to 4 mod 5. You basically find the remainder for the number and then just call that number as mod. You're making sure the 24 lies inside the range of 0 to 5. So how does it help the encryption system? Uh, like when you're encrypting long messages, basically you don't encrypt as ASCII characters. You convert that ASCII characters into a number. We'll be looking at this in the later on RSA encryption systems, but I'm just giving you a brief idea. Basically, you take a text and then you convert it to a number form, and then you start using the number. To make sure that number is secret, you try to use this modular arithmetic so that when you encrypt a number 4 or you encrypt a number 24, the attacker cannot know which number we are actually using. That is the advantage of using this modular arithmetics in normal encryption systems. And for this modular arithmetics, we have additions. Like it's like say it's same a mathematical concept or mathematical field. Uh, Mathematical field where we'll be using all these things. So addition, when you look into addition, you can directly add numbers and perform mod. So let's say I have, can someone tell me what is 6 mod 5 right now in chat somewhere? Yeah, 6 mod 5 is 1. Prajwal, yes. Yes, 6 mod 5 is 1. Then let's say what is 8 mod 5? Yes, 8 mod 5 is 3. So now 6 mod 5 is 1 and 8 mod 5 is 3. Let's say now we have 1 and 3. We can add these numbers directly, which is 6 plus 8 mod 3 is equals to 4 mod 3. Now add what is 6 plus 8? It's 14. What is 14 mod 3? 14 mod 5? 14 mod 5. Yeah, 14 mod 5 is same. And when you do 6 mod 5, you got a 1, and 8 mod 5, you got an 3. And when you add them, you get 4. I hope you understood the all arithmetics behind it. So you can directly add them and do modular arithmetics. There is no issue. We can of adding both numbers and performing the arithmetic modular operation. Whenever the order is, either you add before and do mod, or you do mod and add afterwards, it's the same. The number should strictly lie inside n minus 1. That is the only condition. Coming to subtraction, let's take the same example. So let's say 8, what is 8 mod 5 is 3, and 6 mod 5 is 1. Now let's say what is 8 minus 6 mod 5? Uh, yes, 8 minus 6 mod 5 is 2. Correct. Ajit, yes. No, it's 8 minus 6 mod 5 is 2. Let's say now we know that 8 mod 5 is 3 and 6 mod 5 is 1. 3 minus 1 is 2. So whatever, like, why is the addition the same subtraction? Whatever you do, you can still subtract and then get the same number. You can the operation order doesn't matter. You first subtract and do mod, or do mod and then subtract. You still have to end up the number in the number where you have to lie inside the field of 0 to n minus 1. That is subtraction. When coming to multiplication, yeah, we'll take the same example, 6 and 8. So 8 6 are 48. 48 mod 5 is quick 3. Yes, 48 mod 5 is 3. And we know 6 mod 5 is 1 and 8 mod 5 is 3. And 3 into 1 is still 3. So as above, it doesn't matter when you multiply or whenever you add. So it is the same thing. You multiply first and do mod next, or you do mod first and multiply next, you still end up with the same number. Like you still end up with the same value. The order doesn't matter. These are the basic properties. So in the tricky part is you cannot really perform modular division, because modular division is a different kind of process where like it has some limitations and restrictions. Modular division doesn't work directly. So why will like it is more complicated, as because requiring to find the modular number after the divisor, and like we have to actually do a divided by b, and when you divide those numbers you cannot assure that they always lie in the same field. Yeah, simply we can understand that modular division will not support in this properties. Like there is no modular division, there is addition, subtraction, and multiplication. So these are the basic ground rules we have to remember before we just dive into the session, because RSA algorithm all lies on this algorithm because it is very important. This modular arithmetics is very important for RSA. Yes. Then yes, there is something called modular inverse. Modular inverse, strictly the mathematical definition is a modular inverse is a mathematical concept that refers to finding a number x such that the product of number a and x is congruent to 1 modulo m. I hope everyone knows what congruent is. So, when you take a number a, let's say you take a number a and a variable a number x, arbitrary number x. When you multiply those two numbers and perform a modular operation with the number n, you should end up with the result 1. So it is as good as telling that you have a number a and b, you multiply those two numbers. If at all you get modular of n equals to 1, then you can tell the b is modular inverse of a. So I think this part is clear. If it is clear, then can I get a yes? Or else I'll just recap it again, or I'll just simply reframe it. Okay. Yes. I got one yes. Good. Okay then. So basically there are different ways where you can find this modular inverse. The most easiest way is to just guess the number, which we call as a brute force technique. So we have to find the modular inverse of 3 in mod 7. So what can we do? We'll try to, we'll try to take 3 and then we'll multiply number 1. 3 into 1 is 3. Is 3 mod 7 equals to 1? No. So 3 into 2 mod 7. 3 into 2 is 6. You can, now it is following the multiplication property as we discussed before. 3 into 2 is 6. 6 mod 7 is 6. Still 6. It's not 1. So it's not the inverse. 3 into 3. What is 3 into 3? 9. 9 mod 7. It's 2. Okay, I just have to correct it. Sorry for that. 9 mod 7 is 2. So it is 2 mod 7. It's still not 1. So 3 is not the inverse of 3. Let's look into 3 into 4. 3 fours are 12. 12 mod 5. What is 12 mod 5? 12 mod 7. Sorry, 12 mod 7. Yeah, sorry. 12 mod 7. Yeah, 12 mod 7 is 5. It is still not 1. So it's not the multiplicative inverse. So let's say now we take the next number 3 into 5. 3 into 5 is 15. 15 mod 7 is, yes, 15 mod 7 is 1. So we can happily tell that, or we can confidently tell that 5 is the multiplicative or modular inverse of 3 mod 7. So whenever we take number 3 and 5, we multiply them together and do mod with 7, we end up the result with 1. So modular inverse is the same concept of multiplicative inverse, additive inverse in normal mathematics. See, additive inverse is like when you do some kind of addition, you have to end up with 1. So the additive inverse of 3 is minus 2. Multiplicative inverse of 3 is 1 by 3. All those things, whenever you perform the additive inverse or multiplicative inverse, you just have to end up with the number 1, so that we are sure that that number has the inverse in that existing field. So you'll understand the importance of modular inverse in the later stage when we dive into encryption algorithm. Basically, modular inverse helps us to retain the properties of 3. We can tell that either 3 or 5 is same, because the modular inverse and gives us the same result as 1 mod 7. So these numbers helps us to retain the number each other. So the properties which 3 has, we can confidently tell that the property the same 5 has. So that is how important is modular inverse is. Any doubts? I mean, if you understand modular inverse, just quick yes, we can jump into the next thing. Yes, okay. Okay, yes. So fine. Going to RSA. RSA, RSA has a pretty, it's a very old algorithm. Though it's old, it is still the strongest algorithm we are still using. RSA is actually, stands for, RSA stands for Reverse Shamir and Adelman. These three are the mathematicians or cryptographers who has, invented this algorithm or discovered this algorithm. Basically, one day, what happened was, Robert, yeah, actually, it's Robert Revest. Revest is also like he's an exceptional in problem solving skills. He has the ability to have this cracking codes and things. So one day, Robert receives a letter. The Revest receives the letter from a prestigious university in the city, inviting him to join the team of researchers of a groundbreaking project where already Sam and Alice are already working in this. And then Robert decides to join this team, and then they have worked together and named their team called RSA, and which are named after their initials actually. They have tried like they have put lot of development and lot of resources and lot of knowledge, thinking, and uh, they have spent like literally most amount of time discovering an algorithm where it is simple enough to encrypt and decrypt, and also very secure enough. Since 1977 till today, RSA is one of the strongest algorithm which is in use. RSA is so secure that we are still using those algorithms for encrypting credit cards, encrypting the websites and etc. It is that strong. So coming to the yeah. So RSA is widely used public key cryptography system for securing data transmission. it is, first public key encryption system. So what is public key encryption system? The important term is, uh, the public key, there is two pair of keys where there is public key and private key. Public key is available for everyone. Uh, the key, which the message is used to encrypt. So let's say I have a message called today, the webinar. Now I have to encrypt this webinar link and send it to my friend. I can get his public key online and encrypt that message and send it to him. That is what is public key. And my friend has his own private key where it will be a secret which is known only to him. He'll be encrypting using that private key and then will able to retrieve the message. RSA follows like is the public key encryption system where it has public key and a private key. Yeah, we'll look into this implementation in the coming slides. So based on the mathematical properties, the one of the main key security of RSA is it's based on the prime numbers. I hope everyone uh, yeah, I hope everyone know what prime numbers are. Prime numbers are the numbers which it can divide by itself. Uh, yeah, which can divide by itself. Yes, and 1. So basically prime numbers do not have any factors. So when you multiply two large prime numbers, let's say uh, very large, it's somewhere around 1024 bit length. It's like some 2 to 300 length character string. When you multiply these two numbers together and when you try to factor it, since the number has only two factors which are both prime and very long, it is very hard to factorize by a normal computer. All the factoring algorithms basically work by trying to brute force. So it's like, whenever you're trying to compute it, uh, whenever you give a factor algorithm, let's say I tell factor 10 to the computer, it tries the combination 2 into 2, 2 into 5, 2 into 7, 2 into 10, and then it goes to 2 into 5 matches. Okay, then okay, this can be the exact combination is 2 into 5 is 10. That is how the normal factoring algorithms work. Yeah, there are some efficient algorithms, but that are advanced. So the basic algorithms try to brute force these numbers and find. When the numbers are very large, I mean, let's say like 1024 bit length, which is very large, significantly large, which is around 2 to 300 characters of letters itself. So in those cases, when you multiply that 2 to 300 large numbers, 2 to 300 character large numbers, and then you get a string of equivalent length, and you try to factor those numbers, computers will really struggle to identify what those numbers are. It's not really easy to identify those numbers. That is where the whole core concept of this encryption scheme is working. That is how still RSA is very secure. Yes, as we told, we'll look into the detailed version of how RSA is working. There is first step called key generation, where key generation, as we told, we take two large prime numbers and then we multiply those two large prime numbers and then we choose we multiply and then call it as an n, which is a public exponent. So basically, if I am using two large prime numbers p and q, I'm multiplying it and call it an n. N will be my public factor where this n will be publicly available for everyone. And there is also a public key E, which is, we computed E, it's a random number, but there is a criteria to meet. I'll tell you that criteria while looking into key generation. So N and E are the two numbers which are publicly available. So basically, if you want to send me a message through RSA algorithm, you can look into internet of what my N and E are. And then you can use those N and E to encrypt my messages and send that message to me. So this is how this key generation algorithm works. So yeah, how actually encryption works. So we have a message M. Everyone knows what exponent is, right? 2 power 3, 5 power 10, some 7 power 2000. That is what is exponent. So now we take our message in terms of a number. We take our message in terms, we convert our message into a number and then we try to do, we raise it to power e. So that message will be raised to power e, which is very long, and then we try to perform a mod on that number. So basically you are performing like the equation is m power e mod n. So m power e is the first set of operations where you will be performing, and then you will perform a modular arithmetic on e to make sure the message or the ciphertext which is after encryption lies inside 0 to n minus 1. That is the importance here. See, if I know what e power m directly is, I can directly try to brute force and find what the message is. So to avoid those conditions, we are trying to do the modular arithmetic and narrow down the to narrow down the message length and make it difficult to search for the message. That is how the encryption scheme works. I mean, yeah, it is like a little difficult to understand with slides. I'll show you I'll show you the working example. Then it might be really easy to understand. We have something called E, where we'll try to find the ciphertext. We'll have the ciphertext, then we'll raise it to the power d. Okay, there is a mistake. It is d, and then mod n. So you basically encrypt with public key E and decrypt with public key D. How do we get D? D is, there is something called Euler's quotient. Like, yes, there is a formula to compute this Euler's quotient. So basically, we need Euler's quotient in order to compute D. You can assume, for now layman terms, you can remember that Euler's quotient is something called phi, and phi is equals to p minus 1 into q minus 1. And then you have this phi, you try to find d such that the inverse of, you will try to find a modular inverse between e and d, and you get a d, and that d is the private exponent. Okay, maybe like we'll just dive into the example. So for example sake, we'll just take very small numbers. I hope you can you see my terminal? If you can see, I think a quick yes. So as in the slide, we have P and Q as 3 and 11. So let's say P equals to 3 and Q equals to 11. Okay, sure. I'll zoom a bit.
Manohar?
Yes. Can you, is it fine now?
Yeah, fine now.
Yeah,
Yes.
I think it's fine. Yeah, thank you.
Yes, so yes. So, yes. P equals to 3 and Q equals to 11. And we need N, which is P into Q. So we get N as P into Q. N as P into Q, which is 33. Yes. So after that, we need E. So E is a number which can be taken, which can be taken in random. So, but the condition is E should satisfy a property. For that property, we need phi. Okay. Now let's understand what is phi. Let's say phi equals to phi
Yeah,
is nothing
Manohar,
but P.
I'm
Yes,
sorry to interrupt you. Have you shared
sure.
the screen, or I mean, have you shared the application? Because some people are saying they can't see the screen.
I'm sharing the application. Can
Yeah,
they see
okay,
my
fine. Yeah,
terminal?
then I think it should be visible. Okay, continue, please.
Yes. I mean, if anyone cannot, yes, we are able to see. Okay, fine. P minus 1 into Q minus 1. So just remember the formula of phi as P minus 1 into Q minus 1 for now, because we are just using two prime numbers. But when prime numbers increase, there is a special formula. This is phi is called as Euler's quotient. We can generalize, when we have two prime numbers for RSA, we usually take two prime numbers and then we generate pi, where the phi is the formula is P minus 1 into Q minus 1. This can be generalized. I mean, for RSA, we can use this formula phi as P minus 1 into Q minus 1. we have 5. You know, the condition the E should satisfy is GCD of 5 and comma E should be as 1. Just I have to simplify. I import the yes, this should work. Yeah. So yes. So GCD of 5 and E should be 1. That is the criteria where the E should meet. Let's say if I take E as 4 and see if the GCD is still 1. No. If I take E as 4 and find the GCD between 5 and E, it is 4. It is not really, it's the condition which when the encryption scheme is built is E can be anything, but it should satisfy the condition that GCD of 5 and E is always 1. That is the core condition where it should take care. So now we'll take E as again as 3. Just give me a second. E as 3. So yeah, and then compute GCD. Yeah, it is still 1. Okay. Now we have E, we have N. What do we need now? We need D. How D is nothing but D is nothing but modular inverse of E mod 5. We have to find the modular inverse of E in mod 5. So that is what is D. Since we remember, right? The modular inverse will be having the same property as E. So 3 mod 5, the properties of 3 and 5 are similar. So basically, this will help here. We have to find the modular inverse of E mod 5 in order to get D. So usually if it's a paper-based approach, we try to brute force or use extended Euclidean algorithm. But since we are using there is something called POW. POW in Python, where this is a built-in function where it will compute base star exponent, which is base power exponent, and do the mod for us. So it will basically do the a power e mod n kind of thing. So we can find d easily with power of e comma -1 because it's an inverse. We can write we have as we remembered from the previous slide, we have represented 3 inverse mod 7. I think this slide is visible, right? Yeah, 3 inverse mod 7. Yeah, so we can represent the symbol, which is the same as 3 square mod 7 or 3 power -1 mod 7 is pretty much the same thing. Like pretty much the same convention which we are following. So in Python, we can give e power -1 and mod 5 in order to get D. So now we got D as 7. Now E comma D are the public and private keys, and the public key set is N comma E. Oh, excuse me. Yeah. 33 and 3 are publicly available for everyone. These two values are available for everyone. But the private key here is 7. This is only known to me. Yeah, since you are seeing the session, you people also know, but actually only this 7 is only known to the person who is trying to generate these public keys. Basically, this is what is private. This shouldn't be shared to everyone, because if you know what this is, it is pretty easy to compromise what your message is. Okay, we'll see an example of encryption. Let's say my message is something in the example we have taken as yeah. So we took a message 7, m equals to 7. Now, as we know the encryption algorithm, see, let's call it a ciphertext. Yes, power of 7 comma E comma n. Do you remember what this is? It is basically same as 7 star star, I mean, which is exponent of e mod this thing mod n or percentage n. Yeah, percentage n. So CT is basically same as that. And when you try to decrypt it, you just take now we have D. To decrypt it, we take CT pow of CT comma D comma n, and then you get the message back 7. This is how the encryption and decryption works. So while encrypting, you use the public key E in order to encrypt, and while decrypting, you use the public key D in order to decrypt. That is how the encryption and decryption works. So yeah, see, message power is 7 power 3 mod 33 and 343 mod 33 is 13. When you take 13 and then mod it with 7 and then raise it to the power 7 and then again mod it, you get back the same message. This is the simple encryption and decryption. So coming to security features in RSA, RSA is very strong and it is used for digital signatures. Let me show you a quick example where RSA is being used. Can you see my screen? Now I'm trying to share a website. Yes. Okay.
Yes, yes, we can see it.
Yes. Yes. So there is, usually every website has a certificate. You can, like there is a lock symbol which is on your browser. You can notice that when you click on the lock symbol, it basically shows you what certificate it is using. And in that, this website is using a certificate which is related to RSA. The message, whenever we are browsing through this web page, it basically, uses the RSA algorithm to encrypt and decrypt these, the data which is flowing back and forth. Typically, most websites, not most, many websites use RSA algorithms for RSA certificate algorithms to sign their websites. This is the real life implementations where RSA is being used. And when you notice the credit card transactions also, they look similar to this. So yeah, coming back to the slides. Yeah. So, it relies on the difficulty. RSA every time, see, we have took very small numbers like 3 and 11. We can simply factorize it. RSA always depends on the, the factors which the numbers which we are taking. The more strong the primes are, the more unlikely we can factorize it. So it depends on the factorizing of the large prime numbers. RSA security can is compromised by weak keys. So I'll show you what these weak keys are in our later session. This we can some of the RSA encryption schemes are compromised with those weak keys. And there is something which is advanced cryptography called quantum cryptography, where when quantum computing is on full swing, RSA will be broken. So if anyone who is really interested into this cryptography, please quickly learn these things and try diving into quantum cryptography. That you'll find a really bright future over there. Okay. So coming to weak encryption systems, now we have the message. We are given n equals to 183 and e equals to 3. So n equals to 187 and e equals to 3. So what is the vulnerability here? N is very small. So I can just, there is a factor, simpy dot factor, yes. When I do simpy dot factor in 10, it will give me 187. Yeah. Okay. E equals to 3. So simpy told me what are the factors are. 11 and 17 are the factors of 183. So if you can easily factorize n, the security is compromised. Now you can compute d. D is nothing but power of, e power -1, comma we know 5 as p minus which is p minus 1, which is 11 minus 1 into 17 minus 1. So we know what d is. D is 107. Now we have the ciphertext, which is 130. So ciphertext CT equals to 130. So now we can just do CT power of CT comma D comma N in order to get the message. Yeah, the message is 1. So yeah, he sent the number 1 with using this encryption system, and then we got the ciphertext. This is how we decrypted. The vulnerability here is we have a very small n. That is the disadvantage. We shouldn't have very small n because we shouldn't be able to factorize. That is the disadvantage here. So coming to next, that is one of the vulnerability. Coming to here, the weak here we have a ciphertext CT, and we have a number n. We have a number n, we have a number e. Let me quickly copy these numbers into my terminal. Just give me a second. Yes. So yeah. We know now C equals to this thing, and then n equals to this number, and we know E equals to 3. So in RSA, there is something called low exponent. So basically, whenever you encrypt a message, and after encrypting the message also, if the message still lies inside the n, let's say I took a n as some 1000, 1001. So let's say I'll just go to a new terminal, and then I think you are able to see this right now. Yeah. So yes, let's say n equals to 1000, 1001. Yeah, it's not a prime number. But after encrypting my message, let's say I took a message of m equals to 2 and encrypt it with something called 5. And okay, sure. After encrypting it also, the m is still less than n. In those cases, these kind of vulnerabilities exist. If I encrypt, if I use a very low exponent, it is vulnerable to something called cube root attack. So basically, you can just you can just do the cube root of C. We'll see. For this, we know we need import GMPY2. Yes, and GMPY2 dot iroot C comma yes E. So we have this number long 2 bytes. This number, basically this number is actually encrypted, and this is some garbage value which has been generated, and with this garbage, this is what is encrypted. But the key concept here is, if the message has very low exponent and the ciphertext even after encryption didn't cross over the n, then it is susceptible for these weak exponent attacks. Okay, we'll look into the next P recovery attack, then you will understand like very detailedly. Yes, so cat pen. Okay, yes. Hmm. So cat yeah. Yeah. So there is this key, this is basically the PEM. Normally, when we are signing the websites, or when we are trying to use the signing algorithms, it generates something called pub key and PEM key. So this is how a signature public key looks. From this signature, we are trying to recover what N and E are. This signature basically tells what N and E are. So yes, we have a ciphertext. I think we also have a ciphertext. Yes. Yeah. So crypto.public. Yeah. From crypto, there is something. There is a module called cryptodomes in Python, where it is really helpful for all these cryptography. So key equals to RSA dot import key open dot p public key dot yeah. So we are basically reading this file, and now key dot n has the n value which has been in the public key, and key dot e has the e value. As we see, e is very low. We'll try to decrypt the ciphertext. Yeah, with open encrypt.dat, comma rp as ct equals to f dot read. So basically, I'm just reading the file. Nothing fancy here. Now we'll try to decrypt this. We'll use the same thing. gmp y2 dot iroot ct comma key dot e, which is I'm directly I'm just finding out the cube root. Long bytes too long. I'll tell you. Okay, so when you just print out ct, you look it's in bytes, but basically RSA we have to convert this into number. So there is something called long to bytes to long. So this is a built-in function where bytes to long will convert that this bytes into a message, and now we have this number. Since now we have to do long to bytes, because this this number should be converted back to bytes, and we get a readable plain text, which is flag you got it. That is what is the demonstration. This is how we we try to crack the signature files. So I hope people followed it. Any doubts?
Yeah, Manohar, we've got an interesting question in the chat where one of the
Okay.
participants asks, where did you learn all this from? So you can be honest about
Okay.
it, because even they need to prepare themselves for the CTF.
Yes. So
If you're allowed to be honest about it.
yes. Okay, I'll share you my secret. Basically, I'm really interested into mathematics, and I like computer science. When I was looking what is the domain which is overlapping, then I realized that is cryptography. These all things, when you are searching, you just have to dive into these CTF. CTFs are the one which helped me to learn all these things. I started, I have no idea how to do these things. And when there is a RSA challenge telling, I don't even know what RSA is. Then, after there was a sleepless night researching about what RSA is, and, trying to identify, learn all the algorithms. And since I have a good background in maths, it's not necessary you need to have a good background in maths. But since it made me easy that I have a strong background in modular arithmetics and I understood all these things, you can try to refer, the best way of learning all these things is to play a CTFs a lot. CTFs are the best way to make you understand, learn all these vulnerabilities. And there are resources like, CySecK, these webinars, people do take talks. There are the similar kind of webinars you can find online. And also there is something called CryptoHack, where, that's a platform where everyone, cryptohack.org, where you can learn more about cryptography in that website. These are the places for the beginners to go and learn.
Yeah, I
think
think you
that
can just put
answers the
that
question.
website in the chat.
Sure. Maybe yes. Yeah, I'll put it these resources at the end of the session.
Sure,
Yeah.
thank you. And so, dear
Okay.
participants, like Manohar said, please ensure that you participate in more and more CTFs.
Yes.
And definitely, we hope all of you, we hope to see a great deal of you and a good proportion of you on the other side of the assessment competing in the top 500. So please continue, Manohar.
Yes. So yeah, as Abhishek told, like CTFs. Basically, when you go through online, you'll just get the conceptual knowledge. But CTFs are the place where do you find the real life implementation or the real life vulnerabilities. No one will tell you that there is a small exponent attack in theory. When you look into CTF challenges, okay, you will find okay, so there is something called small exponent attack, and you will try to learn these kind of things or these P recovery challenges. So yeah. Okay, moving on to the AES. AES is, it's easy and it's complicated at the same time. I'll try to explain you as simple as possible. Uh, and AES implementation is nothing. It's all built-in modules. It's not easy to implement AES. There are that hard part has taken care by people who has researched it. So AES is a block cipher. In the RSA, when we are sending messages, it's not a fixed variable length. Basically, the problem arises when the message is not fixed. You might have to develop decryption pattern where you don't know the exact length the message you are receiving. That might be an issue because when you are sending a very huge message, it's let's say some 1,000 or 2,000 characters, and then you try to send that message which is like some 10,000 characters, but the app doesn't support those 10,000 characters. I mean, you can never predict what the length is beforehand. In those cases, block ciphers are really helpful. Block cipher ensures that the message length is always same. Let's say I take a message of 5 characters. It makes sure that it has a fixed length after encryption also. It has the same 5 characters after encryption also. So the developer or the user shouldn't worry what might be the message length or how should I implement this for a variable length message. So basically, coming to AES, AES is symmetric key encryption system. So what is symmetric and asymmetric key? It's a tricky part, where you have to know it. Symmetric key encryption system is where you in symmetric key encryption system like RSA, we use something called E and D, which are different. So basically, you encrypt with a different key and decrypt with a different key. But in AES, you encrypt with the same key and you decrypt with the same key. So basically, the key is the encryption key or the key which you are using is private, and that key used for both encryption and decryption. There is no two different keys like RSA, E, and D. It's not two different keys, it's just one key. As I told you, block ciphers are encryption algorithms that encrypt data in a fixed length blocks, typically using symmetric key, providing a secure communication and ensuring confidentiality, integrity. Yeah, pretty much it is a secure algorithm for say. Moving on, real life examples. I think many of us, watch Netflix, Hotstar, all these kind of things. Yes, right? Yeah, I think everyone do watches. At least, yeah, we watch YouTube, right? So, yeah, basically when this YouTube or this video encoding happens, the fastest way to encrypt and decrypt messages is through AES. The underlying algorithm, YouTube cannot simply straight away send the data like that, or YouTube cannot directly stream, Hotflix you no sorry Netflix doesn't send the data stream directly because someone can intercept the data and then can record it. So to avoid all these things, they are trying to encrypt the network traffic so that the user experience is so safe, and the people who are sniffing the network will not know what they are using. So yeah, one of like few real life examples are securing file systems, OneDrive, Google Drive, all these things try to use these block cipher encryption systems. Have anyone noticed that whenever you try to open WhatsApp, it shows you end-to-end encryption system and it uses AES 256. or AES 128. Maybe whenever, yeah. Oh, mine, great. Okay. So WhatsApp and also these kind of applications use AES and these algorithms because they are pretty fast and they are very secure. Banking and financial algorithms also use these things. Wireless networks like Wi-Fi, WPA, WPA2, and virtual private networks, government, military agencies. These, basically, AES ensures security is the first thing, and speed. Whenever in RSA you might not tell the encryption is fast, but in AES we can assure the speed decryption of the messages. Yeah. So we'll just look into how AES works. Yes. Okay. So this is where the things get a little heated up. Please bear with me. This is a good understanding where yeah, this is a website which is Cryptools. I'll try to share this website afterwards, or I'll try to share the presentation. So let's see how. Basically, AES, just think of a black box. So you send a message into the black box and you have a ciphertext. Like you have a key. The plain text here is the message which you're sending, and you have a key for yourself, cipher key. So you put it into a box, and that box will give some output. That is what is ciphertext. So this is the layman term of AES encryption system. So, it's like you take two things or two numbers, you throw it into a box, and that box will give you a new number, which that box can ensure that it can decrypt. You give that number and the key, it will decrypt the message. So yeah, we'll just look into the animation so that, you can understand it pretty quickly. Let's try to increase the speed. So there is, as we see here, there is something called input state and there is something called cipher key. Basically, input states, the inputs which we are giving are not given in the ASCII characters. We give it in the hexadecimal form. So there is the plain text which we are giving, and there is a ciphertext. So this ciphertext and plain text are given to a box. That box is, that box has few set of operations, which is substitute bytes, shift rows, mix columns, add key rows. All these are like substitute bytes is like, it looks into the table and then it substitute back the value which is there in the table. That is what substitute bytes are. It basically does this thing for every byte present in that. And then we have shift rows, where it will be shifting the rows by 1, by 2, by 3. This is the generic. It is not different for thing. This is the basic implementation of the box which we are talking. And also when it comes to the mix rows, it has some algorithm. It takes a matrix and then do a modular arithmetics on it, and then get a new matrix and then just append it. So it does, and then add this. I think in the last session, we speaker, like that speaker has taken about what XOR is and how is XOR performed. So in add key rows, you perform XOR with the existing thing. Yeah, I mean, these all are just to know how these work. I'm just explaining these. So we just perform this set of operations again and again in order to make sure that these algorithms doesn't be insecure. So basically, when it is 128 bit length algorithm, we perform this add this box operation 9 times. That's standard. And when it is 256 or more, we perform it like 12 times, just to make sure that the secrecy is still maintained. This is the generic implementation. I think I'll just share this site. You can look into the animation and then understand it much more better way. So there are different modes in AES. So likewise, basically AES has different implementations. One is I give the plain text and I use the plain text again and again. So basically you take a block of message, let's say hello world. There is two words. Hello is a five-letter word and world is a five-letter word. So I take hello first, send it, and I use the key and I get the ciphertext. Next I send the world and I use the same key into the box and I get the ciphertext. Now I append these both. So what happens here is whenever I give the message hello, it gives me the same ciphertext. That is where the vulnerability lies. Okay, I'll show you. So, plain text is there, and then we give the key, it puts in a box, and then it gives the ciphertext. It does it individually. For every message, it does it individually. So, whenever you try to encrypt these messages, you get the same output. Uh, I know what this thing is. Can anyone guess what this image is? Yeah, it's a pretty standard image where everyone should know. It's a penguin, but which penguin is that? Yeah, it's a penguin, Linux. Yeah, it's a Linux penguin. Yeah, So whenever, like, one of example is when you encrypt this Linux penguin with ECB mode, you notice that all the black color has been in the same color. Did you notice here? I'll zoom a little bit here. Yeah, okay. I think we have moved away from the site. Yes. So wherever it is black, it's a blue. Did you notice? Wherever it is white, it's little yellow. So basically, what it is doing it whenever it is finding white, it is encrypting in the same way. ECB mode tries to security is like, whenever you give the same message, it gives the same output. So basically this encryption, let's say it's by pixel. Whenever I'm giving black, it's still giving me blue output. Whenever I give black, it is still giving me blue. That is the major disadvantage with ECB mode. The secure, it is encrypting the message, but the privacy is not so secure. Like, I mean, if you have strong amount of plain text and ciphertext, you can map it and then you can crack the ECB mode. So this is one of the disadvantages of ECB mode, and this is how ECB mode works. Let's look into quick implementation of ECB mode. So, as I told you, it's most of the work has been done by already when these people who are doing it. So there is modules which are there existing. So, okay, just give me a second. So there is, as I told you, please explore the module crypto.cipher crypto PyCryptodome while using. It will be really helpful during your CTF solving challenges. You can install it with pip PyCryptodomes, or you can just go to online and see PyCryptodomes, and you'll be knowing this this library. It has most of the cryptographic implementations. So yeah, from crypto.cipher, I'm importing AES, and from crypto.utils.pad, I'm importing padding to make sure that the message is padded exactly with the right amount of padding is nothing but, you say we say that padding is a random characters, you add after your message to just ensure that the length of the message matches equally. Let's say the length of the message should be 16, but hello world is only 11 characters. Those rest 5 characters will be some random bytes or some plain text, some random spaces, in order to ensure that the message length is 16. The message length is 16. That is how padding and unpadding helps us. So yeah, now yes. Now I'll try to import get random bytes. So this is, I am key. I'll just show you the key. This key get random byte 32. It is getting me a 32 random byte length of 32. And then data is nothing but hello world. We have to take those in bytes. Usually when we are encrypting and decrypting messages, don't try to take it as strings, try to take it as bytes. Coming to encryption, yes. So what we are trying to do is, cipher equals to new AES.key.ECB mode. We are AES.mode CBC or EBC helps you to understand like which mode it is. We can, in the same way we can use ECB here. I'll show you. Wait. So AES dot mode. We have CBC, we have CMMC, we have all this. Like there are different kinds of mode which you can work on. Please try to explore all those modes if you have time. So basically when we are encrypting ciphertext, yeah, ciphertext. So it has encrypted the data with the ciphertext and the block size which we have given. Now IV is what we have taken. Like we have taken a random IV. This is what we are using it. We are using to generate an IV as a secret key. So let's so we have generated a ciphertext like this. How do we decrypt it? I'll just quickly show how to decrypt it. So decryption is also same, like why likewise it has encrypt. We have something called decrypt also. So decrypt data is equals to cipher.decrypt ciphertext AES block set which is mentioned, and unpad. We are using unpad because we have added the padding data. So basically to get that padded data removed, we are using that unpad. See, the ciphertext became a byte which is garbage, and when I decrypted it, I got the same message, hello world. So yeah, like this is the standard example of how AES works. This is the implementation. This might be a little difficult to grasp right away. As I told you, I'll put the crypto link. Please try to look into that link and try to. Trying to if you are facing any troubles while using it in your compiler or using in your Python, there is something called Sage cell server. Please go to this site, and this is a very powerful IDE, or you can kind of call a compiler, which is Python. You can try to run like huge computations also easily on online. If you're facing any issue, just go to this website and try running all those tools. It will help you to work. Yeah, that is how is implemented encryption and decryption. Yes, that's it for the session. I mean, does anyone have any doubts to point out, or anything you want to know related to this AES or RSA? Yeah. Also, maybe anything related to, okay, I'll try to quickly show you the resources or share the resources link on chat. I'm just stopping my screen share. Mm, okay. This is the presentation, and also yeah. Okay. These are the resources which you can use, and also I'll yeah, these try to, yeah. I think these resources should help you to solve the CTF challenges. And also there is something called this yeah, crypto hack org. You can try it over there, trying crypto challenges, basic level crypto challenges, and yeah, that is how. I think if anyone has any questions, I'm ready to answer. I'm open to answer. Anything, not just today's session, anything how to
Kaushik,
learn.
can you please take a look at the Q&A section?
Hi. There is no questions in Q&A section.
Okay.
Yeah.
It means either they have understood completely,
Understood
or
all?
they have.
Yeah, so we request the participants, we
Yeah, we
just
can
wait
say.
for a few minutes more. We
Yeah.
request the participants to please put in your questions in the Q&A section.
Yeah, I mean, if you people are at least active, just spam the chat box. At least we'll know that you are
No,
on
that they are,
live.
that they are active. There's
Yeah.
no doubt about that.
Yeah.
But I'd request all the participants to please post their questions in the Q&A section.
These will these be resources to be good enough for the mathematics behind crypto? I would suggest you, whenever you are getting any mathematical concepts, don't directly, there might not be a clear explanation. Try to look into the related things. Like, let's say RSA, when you look into the resources, they'll tell you it is using modular arithmetics, but no resource will tell you what modular arithmetics is. So try looking into those key terms and then try understanding those algorithms. So whenever you're trying to solve a CTF challenge in a similar way, like in your upcoming CTF, try to look into the key terms. So, the description might be, okay, the exponent might be really low, or the things like, in the description part, they are tricking you to give you a hint related to the challenge. Try to understand those things and then just look for the key terms or look for the similar write-ups which are provided online. Are how one should learn Python, mainly focusing to cryptography. It's if you know basic Python coding, it's good enough to learn cryptography. It comes with experience. If you ask me, just play CTFs, keep on playing CTFs. You will be learning this coding part. Are there any career paths related to cryptography? Yes, there are many. If
Oh,
you
there would be many career paths, but for that, I think even to clear the interview, you need to participate in many CTFs so that you
yes,
can answer
yes,
questions regarding all the scenarios.
yes. Can you suggest any books for
How
cryptography?
do
No,
you open
I
the
don't
Python
really.
shell?
Oh, okay. How
What
did
shell
you
is
open the
in the chat?
Python shell? Yeah, there is something called IPython 3, or you can. I would suggest you to use Sage. I'll quickly share you the Sage cell. Sage cell is really powerful. Even it's a little advanced tool, but I would suggest you to start using Sage Sage shell right away so that you can get a good grasp on it. What Python library is related to cryptography? There are many, but the usual one is like PyCryptodome. Dome is what usual CTFs we use for CTF related things. We can use PyCryptodomes. How to get started? Start cryptography. Yeah, you just have to need the motivation and the support and workshops. Try attending workshops, play CTFs. You are good to go. You are good into cryptography.
Yeah, there is one question regarding the cryptography only.
Yeah.
What are real life
Yes.
attacks associated with cryptography?
Uh, yeah, like real life attacks, basically these vulnerabilities come in the implementation. See, now usually developers, when they are developing the application, they don't really care about the security functions. They just implement AES block and go away. But it is the job for the security researchers like us to ensure that those encryption schemes are secure. Like these kind of vulnerabilities basically come with the implementation of bad coding or improper awareness of how to encrypt data. That those are the usual vulnerabilities which you can find in the real world life. Yes. Any other questions? Mm,
No.
yes.
Okay, so I think with that we have come to the close of this
Yeah.
very, very interesting 8th Masterclass webinar as part of the Digital Defenders Capture the Flag competition 2023. I'd like to thank our young and energetic speaker, Mr. Pagilla Manohar Reddy, for delivering this webinar. And I think the most important takeaway that we have been getting as organizers is that your webinar is the one where students have understood at least 80 to 100% of the content. So that itself is a
Thank you.
testament to how nicely you've
Yeah.
packaged and delivered the webinar. But dear participants, I would request all of you to please, I hope all of you have paid attention to the different concepts that Manohar has spoken about, and going at about the 3 approaches or 3 concepts per webinar, that would give a total of 24 approaches or 24 concepts, which are going to be very important for all of you to follow if you want to crack the CTF. So we have an assessment coming up, and the assessment is live now. So I have posted the link to the assessment in the chat box. I request all of you, please copy it. So the assessment shall remain open until 5 p.m. tomorrow evening. So until 5 p.m. on the evening of 1st July, which is Saturday, and this will be the final assessment. So after you complete this assessment, we will tally all the assessment scores of the CTF registrants, and only the top 500 who qualify shall be invited for the CTF intro session on the 5th of July. We have the CTF intro session on the 5th of July, which will be held by experts from Team BIOS, like I already mentioned in the introduction to this webinar, which is the premier CTF team in India. So they will be there to answer any of your queries and to discuss the format and delivery of the CTF and how you guys can go about participating in it. Okay, we will also be pasting this assessment link on the webinar homepage for the homepage of the webinar by Manohar on the CySecK website. And I shall post that link in the chat box in just a few moments. And in the meantime, Manohar, if you have anything else to say, please go ahead.
Yeah, like I just want to, I just want you to see in the finals. Hope you do well in the CTF. Just want to wish you best of luck for your CTF. And yeah, maybe crypto can help you getting into this top 500 and win those amazing prizes which is mentioned. It's really a great opportunity. Try, it's really, I'm really, happy to see these many participants who are interested and then learning towards the cybersecurity field. I wish you all the best for your upcoming CTF and also your upcoming career. Thank you. That's it.
Thank you very much, Manohar, for that very, very energetic webinar. I think it was an apt webinar to round off the series of webinars. And, we are getting a lot of positive vibes even from the participants, and all the participants were quite involved, and, they understood everything practically that you delivered. What more can we ask for? So you can sign off now, and I will just convey the information regarding the assessment, and I will close the webinar.
Okay. Thank you very much. Bye. Yeah.
So dear participants, I am now going to paste in the chat box the link to the webinar homepage. Yeah, so that is the link to the webinar homepage. On this webinar homepage, you will be able to find the link to the assessment, which will remain active until 5 p.m. tomorrow evening. That is on the evening of Saturday, 1st July 2023. We request all of you to please ensure that you attempt the assessment within this time, as we will stop accepting responses after 5 p.m. And in case you wish to revise your concepts, in case you wish to go through the webinar again, or have not been able to attend the webinar live due to certain prior academic commitments, we would be posting the recording of this webinar on CySecK's YouTube channel within about 2 to 2.5 hours from now. We request you to please bear with us. And you are most welcome to view the recording once again, clarify your concepts, and give your best shot at the assessment. Yeah, so we are getting a question in the chat box asking how to contact us later in case of any questions about the topic. Well, in case of any questions, you can just write to us at the mail ID that.
You can post your queries on Telegram only.
Yeah, that would be better actually. We request you to please post your queries on Telegram, and I think we would be better positioned to answer them right there. That's a very useful suggestion given by Mr. Kaushik from our team. So I will now stop the recording and close the session. I hope all of you have copied the link to the webinar homepage as well as the link to the assessment. I wish all of you the very best in the assessment, and I look forward to seeing most of you on the other side when the CTF begins for the CTF introductory session on the evening or afternoon of 5th of July. Thank you and all the best.